Hello everyone, in this video we'll discuss about the characteristic table and excitation table of SR flip-flop. First we'll see what is a characteristic table and what is excitation table. A characteristic table defines the logical properties of a flip-flop by describing its operation in tabular form. They define the next state as a function of the inputs and the present state. So next state is the state that results from a clock transition. So if we are taking the SR flip-flop, then the characteristic table of the SR flip-flop will include the next state as a function of inputs and the present state. So the next state will be Qn plus 1 and the present state is, we are considering the present state as Qn. So for an SR flip-flop, the inputs will be S and R. So we will define the next state, that is Qn plus 1, in terms of S and R and Qn. So that is called the characteristic table. So for an SR flip-flop, will be representing Qn plus 1 in terms of Qn, S and R. So this table is called the characteristic table. Next is the characteristic equation. Characteristic equation means the logical properties of a flip-flop as described in the characteristic table can be expressed algebraically with the characteristic equation. So here in this table we are writing Qn plus 1 in terms of Qn, S and R. We are writing in a tabular form. So if we write Qn plus 1 in terms of Qn, S and R in algebraic form, then that is called the characteristic equation. So we can draw the K-map corresponding to Qn plus 1 and we will get the simplified logical expression corresponding to Qn plus 1 in terms of Qn, S and R, and that will be the characteristic equation. Next is the excitation table. Excitation table means a table showing the required input conditions for every possible transition of a flip-flop output. That is, it will be showing the input conditions for every possible transition of a flip-flop output. So if the output is having transition from Qn to Qn plus 1, that is if the present state is Qn, the output is having transition to the next state, that is Qn plus 1. So corresponding to Qn and Qn plus 1, different values of Qn and Qn plus 1, what is the input condition? Okay, so that will be shown in a table and that table is called excitation table. So if we are taking the excitation table, if we are taking Qn and Qn plus 1 and we are writing the input conditions of J and K, we are writing the input conditions J and K, then that will be the excitation table of JK flip-flop. Okay, so now we'll see the excitation table and characteristic table of a SR flip-flop. So this is the truth table of an SR flip-flop. So as you can see over here, if there is no clock, then whatever be the values of S and R, the output Qn plus 1 will be equal to Qn. That is, it acts as memory or hold. Next is in the all other four stages, in all the other stages, clock input is present, and I am showing a positive edge triggered clock pulse over here. We can show a negative edge triggered clock also. So there will be four possible combinations of S and R: 0, 0, 0, 1, 1, 0 and 1, 1. And we know that when S and R is 0, then Qn plus 1 will be equal to Qn. That is, whatever is the state before applying clock, that will be retained. That is, it will be acting as memory. And if S is 0 and R is 1, then the output Qn plus 1 will be equal to 0. That is, R is high, corresponding to that, the output will be reset or it will be set to 0. And corresponding to S is equal to 1 and R is equal to 0, the output is high. That is, S is equal to 1, set input is 1, so the output is set, or Qn plus 1 is equal to 1. And 1, 1 condition corresponding to S is equal to 1, 1 condition of S and R is the invalid condition. So if S and R are 1, 1, then that will be invalid for an SR flip-flop. Now we can draw the characteristic table. So in the characteristic table, we will be writing Qn plus 1 in terms of Qn, S and R. So there are three inputs, Qn, S and R. So there will be 8 possible combinations: 0, 0, 0, 1, So we will see what is Qn plus 1 corresponding to each condition. So the first case is S is 0 and R is 0. So S is 0 and R is 0 means it is this condition, and Qn is 0, that is the present state is 0. So the next state Qn plus 1 will be also equal to 0. It is this condition. So we know that Qn plus 1 will be equal to Qn. So Qn is 0. So Qn plus 1 will also be equal to 0. Next case is 0, 1. So if S is 0 and R is 1, then the output will be reset, or it will be equal to 0. Next case is 1, 0. So then the output will be set, or Qn plus 1 will be equal to 1. And this is 1, 1. This 1, 1 corresponds to an invalid state. So we can write a don't care over here. Next is S and R are 0, 0. So Qn plus 1 will be equal to Qn corresponding to this condition. So Qn plus 1 will be equal to Qn. Qn here is 1. So Qn plus 1 will also be equal to 1. Next case is 0, 1. So corresponding to 0, 1, it does not depend on Qn. The output will be reset. So that will be equal to 0. 1, 0, the output will be set. It will be 1, and corresponding to 1, 1, it is an invalid state. So we are putting a don't care. Now we can find the expression for Qn plus 1. We can write the algebraic equation, characteristic equation, not the algebraic equation. We can write the characteristic equation from the characteristic table. So that is, we have to write the equation for Qn plus 1. So we can draw the K-map for that. So we have to draw a 3-variable K-map. This is Qn and this is S and R. So 0, 0, 0, 1, 1, 1, 1, 0, and this corresponds to 0 and 1. So corresponding to 0, 0, 0, Qn plus 1 is, this is the K-map for Qn plus 1. So corresponding to 0, 0, 0, Qn plus 1 is 0. Next 0, 0, 1, it is 0. Next 0, 1, 0, it is 1. 0, 1, 1, don't care. 1, 0, 0, 1. 1, 0, 1, 0. 1, 1, 0, 1. 1, 1, 1, don't care. Now we can do the grouping. So this four cells can be grouped together, so that this forms a quad. Now this one can be grouped with this one. So the expression will be, this is equal to, here 1 is common in these two cells. So that is equal to S, and here in the first and the last column 0 is common. So we can write R bar, and here it is Qn. So we can write the expression for Qn plus 1 as S or Qn R bar. So that is the characteristic equation. Now we are going to write the excitation table. So we will be writing the excitation table from the characteristics table. So we will be writing what is S and R from Qn and Qn plus 1. We will find the values of input conditions. We will find the input conditions from the values of Qn and Qn plus 1. So there will be 4 possible combinations: 0, 0, 0, 1, 1, 0 and 1, 1. So correspondingly we can look at the characteristic table. So the first condition is 0, 0. So corresponding to this, Qn is 0, Qn plus 1 is 0. So here also in the characteristic table, Qn is 0 and Qn plus 1 is 0. So the S value is 0 corresponding to these two cases. Qn is equal to 0 and Qn plus 1 is equal to 0. S value is 0. But R value is 0 for one case and 1 for the other case. So we can write R as don't care and S as 0 corresponding to Qn equal to 0 and Qn plus 1 equal to 0. Now next is Qn equal to 0 and Qn plus 1 equal to 1. So we can check for that case over here. So here Qn is 0, Qn plus 1 is 1. So only one state is there, 0 from 0 to 1. So correspondingly S is 1. Here S is 1 and R is 0. Next case is 1, 0. So we can look for the case 1, 0. So Qn is 1 and Qn plus 1 is 0. So it is this case. So correspondingly we have S is equal to 0 and R is equal to 1. And the last case is 1, 1. So corresponding to 1 1, 1 1 is, this is 1 1, Qn is 1 and Qn plus 1 is 1, and this is also 1 1. So for these two cases we have this is our S corresponding to 1 1, that is it is 0 for one case and 1 for the other case, and it is R as 0 for both the cases. So we can write R as 0, but S is 0 for one case and 1 for the other case, so we can write S as don't care. So this is the excitation table. So from the characteristic table we have written the excitation table. So for 0 0 it is 0 don't care. So 0 1 it is 1 0, 1 0, S value is 0 and R value is 1, and corresponding to Qn equal to 1, Qn plus 1 equal to 1, S is don't care and R is equal to 0. So one way of remembering this, we have to remember the excitation table for the flip-flop conversion. We have to convert one flip-flop to other. So for that we'll be using this excitation table and characteristic table. So we have to remember these things, and also we'll be using this excitation table for the counter design also. So one way to remember this is, if you look on this S, we can see that S is 0 1 0 X and R is 0 1 0 X in this pattern. That is, if we move from top to bottom, for S it is 0 1 0 don't care, and if we move from bottom to top for R, then it is 0 1 0 don't care. So we can remember it like that. So this is about the characteristic table and excitation table of